Okay, hi everyone, welcome back to this video series on data centers. Introduction to TCP. Because TCP is so central to working with the internet and intranets, it's essential for you to understand it in detail. I'll begin by giving you some background on TCP/IP and how it came about, and then move on to describing the important technical goals defined by the original designers. After that, you'll find out how TCP/IP compares to a theoretical model, the Open Systems Interconnection OSI model. A brief history of TCP/IP. TCP/IP first came on the scene in 1973. Later in 1978, it was divided into two distinct protocols, TCP and IP. Then in 1983, TCP replaced the Network Control Protocol NCP and was authorized as the official means of data transport for anything connecting to ARPANET, the Internet's ancestor that was created by ARPANET, the DoD's Advanced Research Projects Agency, way back in 1957 in reaction to the Soviets' launching of Sputnik. ARPA was soon redubbed DARPA, and it was divided into ARPANET and MileNet, also in 1983. Both were finally dissolved in 1990, but contrary to what you might think, most of the development work on TCP/IP happened at UC Berkeley in Northern California, where a group of scientists were simultaneously working on the Berkeley version of Unix, which soon became known as the BSD, or Berkeley Software Distribution Series of Unix versions. Of course, because TCP/IP worked so well, it was packaged into subsequent releases of BSD Unix and offered to other universities and institutions if they brought the distribution tape. So basically, BXD Unix bundled with TCP/IP began as shareware in the world of academia, and as a result became the basis of the huge success and exponential growth of today's internet, as well as smaller and private corporate intranets. As usual, that may have started as a small group of TCP/IP aficionados involved, and as it did, the US government created a program to test any new published standards to make sure they passed certain criteria. This was also to protect TCP/IP's integrity and to ensure that no developer changed anything too dramatically or added any proprietary features. It's this very quality, this open systems approach to the TCP/IP family of protocols that pretty much sealed its popularity, because it guarantees a solid connection between myriad hardware and software platforms with no strings attached. TCP and the DoD model. The DoD model is basically a condensed version of the OSI model. It's comprised of 4 instead of 7 layers: process application layer, host-to-host layer, intranet layer, network access layer. Figure 4.1 shows a comparison of the DoD model and the OSI reference model. As you can see there, the two are similar in concept, but each has a different number of layers with different names. A vast array of protocols combine at the DoD model's process application layer to integrate the various activities and duties spanning the focus of the OSI's corresponding top 3 layers: application, presentation, and session. We'll be looking closely at those protocols in the next chapter. The process application layer defines protocols for node-to-node application communication and also controls user interface specifications. The host-to-host layer parallels the functions of the OSI's transport layer, defining protocols for setting up the level of transmission service for applications. It tackles issues such as creating reliable end-to-end communication and ensuring error-free delivery of data. It handles packet sequencing and maintains data integrity. The internet layer corresponds to the OSI's network layer, designating the protocols relating to the logical transmission of packets over the entire network. It takes care of the addressing of hosts by giving them an IP Internet Protocol address, and it handles the routing of packets among multiple networks. At the bottom of the DoD model, the network access layer implements the data exchange between host and network. The equivalent of data link and physical layers of the OSI model, the network access layer oversees hardware addressing and defines protocols for the physical transmission of data. The DoD and OSI models are alike in design and concept and have similar functions in similar layers. Figure 4.2 shows the TCP IP protocol suite and how its protocols relate to the DoD models. In the following sections, we'll look at the different protocols in more detail, starting with process application layer protocols. The process application layer protocols. In the following sections, I'll describe the different applications and services typically used in IP networks. The following protocols and applications are covered: Telnet, FTP, TFTP, NFS, SMTP, POP, SNMP, SSH, HTTP, HTTPS, NTP, DNS, DHCP, BootP. Telnet. Telnet is the chameleon of protocols. It's specifically and is terminal emulation. It allows a user on a remote client machine called a Telnet client to access resources of another machine, the Telnet server. Telnet achieves this by putting a fast one on the Telnet server and making the client machine appear as though it were a terminal directly attached to the local network. This projection is actually a software image, a virtual terminal that can interact with the chosen remote host. These emulated terminals are of text mode type and can execute defined procedures such as displaying menus that give users the opportunity to choose options and access the applications on the DoD server. Users begin a Telnet session by running the Telnet client software and then logging into the Telnet server. File Transfer Protocol (FTP). File Transfer Protocol (FTP) is the protocol that actually lets users transfer files, and it can accomplish this between any two machines using it. But FTP isn't just a protocol, it's also a program operating as a protocol. FTP is used by applications as a program. It's employed by users to perform file tasks by hand. FTP also allows for access to both directories and files and can accomplish certain types of directory operations such as relocating into different ones. Accessing a host through FTP is only the first step, though users must then be subjected to an authentication login that's probably secured with password and usernames implemented by system administrators to restrict access. You can get around this somewhat by adopting the username anonymous, though what you'll gain access to will be limited, even when employed by users manually as a program. FTP's functions are limited to listing and manipulating directories, typing file contents and copying files between hosts. It can't execute remote files as programs. Trivial File Transfer Protocol. Trivial File Transfer Protocol is a stripped down stock version of FTP, but it's the protocol of choice if you know exactly what you want and where to find it. Plus, it's easy to use and it's fast too. It doesn't give you the abundance of functions that FTP does, though TFTP has no directory browsing abilities. It can do nothing but send and receive files. This compact little program also skims in the data department, sending much smaller blocks of data than FTP, and there's no authentication as with FTP, and it's even more insecure. Few sites support it because of its inherent security risks. Network File System (NFS). Network file system is a jewel of protocol specialization. In file sharing, it allows two different types of file systems to interoperate. It works like this. Suppose the NFS server software running is on a Windows server and the NFS client software is running on a Unix host. NFS allows for a portion of the RAM on the Windows server to transparently store Unix files, which can in turn be used by Unix users, even though the Windows file system and Unix file system are unlike. They have different case sensitivity, file name length security, and so on. Both Unix users and Windows users can access the same file with their normal file systems in their normal way. Simple Mail Transfer Protocol SMTP. Simple Mail Transfer Protocol SMTP answers our ambiguous call to email. Uses a spooled or queued method of mail delivery. Once a message has been sent to a destination, the message is spooled to a delivery, usually a disk. The server software at the destination posts a visual, regularly checking the queue for the message. When it detects them, it proceeds to deliver them to their destination. SNMP is used to send mail. POP3 and IMAP is used to receive mail. Post Office Protocol. Post Office Protocol gives us a storage facility for incoming mail, and the latest version is called POP3. Sounds really basically. How this protocol works is when a client device connects to a POP3 server, messages addressed to that client are released for downloading. It doesn't allow messages to be downloaded selectively, but once they are, the client-server interaction ends and you can delete and tweak your messages locally at will. Lately, we're seeing a newer standard, IMAP, being used more and more in place of POP3. Simple Network Management Protocol, SNMP. Simple Network Management Protocol collects and manipulates valuable network information. It gathers data by polling the devices on the network from a management station at a fixed or random intervals, requiring them to disclose certain information. When all is well, SNMP receives something called a baseline, a report eliminating the operational traits of a healthy network. This protocol can also stand as a watchdog over the network, quickly notifying managers of any sudden turn of events. These network watchdogs are called agents, and when aberrations occur, agents can send an alert called a trap to the management station that contains information such as CPU or interface utilization, up-down status, terminal statistics, and more. Secure Shell SSH. Secure Shell SSH protocols set up a secure Telnet session over a standard TCP IP connection and is employed for doing things like logging into systems, running programs on remote systems, and moving files from one system to another. And it does all this while maintaining a nice, strong, encrypted connection. You can think of it as the new generation protocol that's now used in place of RSH or login event Telnet. Hypertext Transfer Protocol, HTTP. Although snappy websites comprising a million of graphics, text, links, and so on the Hypertext Transfer Protocol, HTTP, is making it all possible. It's used to manage communication between web browsers and web servers and opens the right resource when you click a link, wherever the resource may actually reside. Hypertext Transfer Protocol Secure, HTTPS. Hypertext Transfer Protocol Secure, HTTPS is also known as Secure Hypertext Transfer Protocol. It uses secure sockets layer SSL. Sometimes you'll see it referred to as SHTTP or SHTTP, which is an extension of HTTP and doesn't use SSL, but no matter, as indicated, it's a secure version of HTTP that arms you with a whole bunch of security tools for keeping transactions between a web browser and a server secure. It's what your browser needs to fill out forms, sign in, authenticate, and encrypt an HTTP message when you make a reservation or buy something online. Network Time Protocol (NTP) to synchronize the clocks on our computers to one standard time source, typically an atomic clock. Network Time Protocol (NTP) works by synchronizing devices to ensure that all computers on a given network agree on the time. This may sound pretty simple, but it's very important because so many of the transactions done today are time and date stamped. Think of your precious databases from one. It can mess up a server pretty badly if it's out of sync with the machines connected to it, even by a mere second. You can't have a transaction entered by machine at say 1:50 a.m. when the server records this transaction having occurred at 1:45 a.m. So basically NTP works to prevent from bringing down the network. Very important indeed. Domain name service (DNS). Domain name service DNS resolves host names, specifically internet names such as www.hypertp.ie. You don't have to use DNS. You can just type in the IP address of any device you want to communicate with. An IP address identifies the host on the network and the internet as well. However, DNS was designed to make our lives easier. Think about it. What would happen if you wanted to move your web page to a different service provider? The IP address would change and no one would know what the new one was. DNS allows you to use a domain name to specify an IP address. You can change the IP address as often as you want and no one will know the difference. DNS is used to resolve a fully qualified domain name (FQDN). For example, www.hypertp.ie or hypertp.ie. FQDN is a hierarchy that can logically locate a system based on its domain identifier. If you want to resolve the name HyperTP, you either must type in the FQDN of toddlamel.com or have a device such as a PC or router add a suffix for you. For example, on a Cisco router, you can use the command IP domain name lamel.com to append each request with the lamel.com domain. If you don't do that, you'll have to type in the FQDN to get the DNS to resolve the name. Dynamic Host Configuration Protocol. Bootstrap. Dynamic Host Configuration Protocol (DHCP) assigns IP addresses to hosts. It allows easier administration and works well in small to even very large network environments. All types of hardware can be used as a DHCP server, including a Cisco router. DHCP differs from BootP in that BootP assigns an IP address to a host, but the host's hardware address must be entered manually in a BootP table. You can think of DHCP as a dynamic BootP, but remember that BootP is also used to send an operating system that a host can boot from. DHCP can't do that, but there is a lot of information a DHCP server can provide to a host when the host is requesting an IP address from the DHCP server. Here's a list of the information that a DHCP server can provide: IP address, subnet mask, domain name, default gateway, routers, DNS server address, WINS server address. A DHCP server can give us even more information than this, but the items in the list are the most common. A client that sends out a DHCP discover message in order to receive an IP address sends out a broadcast at both layer 2 and layer 3. The layer 2 broadcast is all F's in hex, which look like this: FF, 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 FF. The layer 3 broadcast is 255.255.255.255, which means all networks and all hosts. DHCP is connectionless, which means it uses user datagram protocol (UDP) at the transport layer, also known as the host-to-host layer, which we'll talk about next. Here's an example of the output from my trusty analyzer: Ethernet 2 source 00, B DB99D35E destination broadcast FF Internet broadcast SRC 0.0.0.0 0.0.0.0 DST, which is destination 255.255.255.255 255.255.255.255. The data link and network layers are both sending out all hands broadcast saying help, I don't know my IP address. DHCP client four-step process, client broadcast DHCP discover, server unicast DHCP offer, client request DHCP request, server unicast DHCPK. Okay, so I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.